Hi, welcome to Data Structure and Algorithm series by Coding Ally. Coding Ally is a non-profit organization where we believe women and gender minorities should have a safe space and support system where they can foster their skills and careers in tech. I'm your host Sue. Today, we are solving this Leetcode problem 235, lowest common ancestor of a binary search tree. So this is the agenda. First, I will read the problem statement and go through the thought process and some theory behind. And then after that, I will go through the approach. So there are a few approaches that we can use to solve this problem. Recursive, iterative, pathfinding using breadth-first search or depth-first search. So out of these approaches, in this video, I will go through the recursive approach. So this is the problem statement. Given a binary search tree, find the lowest common ancestor LCA of the two given nodes in the BST. According to the definition of LCA on Wikipedia, it is the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T, that it has both P and Q as descendant. In here, where we allow a node to be a descendant of itself. So for that part, I will go through the example in detail. So let's have a look at this example. In this example 1, we see that we have got this binary tree. So when we are given the binary tree, we have got this in array. So for the binary tree, a binary search tree, in the given array, you can read it like this. 6 is the root, and then from left to right. So you go that in the traversal breadth first search. So you go first level 0, level 1, level 2. So 6, 2, and then after that 8, and then 0, 4, 7, 9, like this. So we are given this root, this binary search tree, and we are given these two values 2 and 8. So from here, from the visual observation, we can see that P is 2, Q is 8, the lowest common ancestor, which is 6. So this is the output. Let's have a look at example 2. So in this example, the binary tree is still the same, but the P and Q value is different. So in this case, P is 2 here and Q is 4 here. So from here you can see that this P is the root, because root 2, it is the root, it is a node, it can be a descendant of itself according to the LCA definition. So because of that, the root is 2. Okay, let's have a look at example 3. In example 3, we only have two nodes, so 2 and 1. So as per the binary search tree, if we were to construct it, it will be like this. So 1 is less than 2, the root node, so it is on the left side. So from here, we can see that 2 is the root. So let's have a look at the constraint. The constraint is the number of the nodes in this tree is in the range between 2 and 10 to the power 5. And the value itself is between minus 10 to the power 9 and 10 to the power 9. And all in here, the key thing is all the node value, all of these values, they are unique. And P and Q, they are not the same. And it is guaranteed that P and Q will exist in the given binary search tree. So these are all the constraints. So before I go on, I want to summarize the 3 cases that we have observed. So in the case 1, we have seen that in the given binary search tree, P and Q, P can be on the left side, Q can be on the right side, or vice versa. Also, no. So I'll go again. In this example, case 1, P and Q. So in this first case, P is the root. The node is a descendant of itself, so 6 and 2. So in here, the root is 6. In case 2, in here, as you can see, P is 8, Q is 9, so 8 is the root. So that's the case 2. In case 3, it is where we find P and Q, they are on the left subtree and on the right subtree. So in this case, 6 is the root. So these are the 3 cases that I want to highlight before going on. So before we go on, let's understand what is the binary tree, binary search tree? So binary tree is a tree with at most 2 children for each parent. So we also have, you know, tertiary tree, ternary tree. So it will have 3 children. Quaternary tree, it will have 4 children. Or n-ary tree, it can have n children. But in binary tree, it has maximum 2 children. So binary search tree, it is a variant of the binary tree. So what is the difference? So this is the difference. The difference is, as you can see in here, left child value, or the node of the left child value, it has to be less than or equal to the parent value. The same goes for the right child value. The right child value have to be either greater or equal to the parent value, as we have seen in this binary search tree. So in this video, we are going to use the recursive approach to solve this particular problem. So the question we need to ask ourselves is, why can we solve this problem using the recursive approach? So this is the answer. So first we have to understand what is the recursive data structure. Recursive data structure is a data structure that is partially composed of smaller or simpler instances of the same data structure. Let's have a look at how this definition applies in the binary tree. In the binary tree, it can be empty tree with null, or it will have a node and it will have 2 subtree, a left subtree and right subtree. So we know that binary search tree is a variant of a binary tree. So let's have a look at it. So if we break it down as a recursive data structure for this binary search tree, you can see now the whole tree is the binary search tree, and we can break it down into left subtree and right subtree. And in here, we can further break it down into left subtree, right subtree for the 2, and on this side again, 8, we can break it down into left subtree and right subtree. And I have changed the color, the leaf color, which leaf node, this color into green color, because it is a leaf node. It has no further child node, so they are all leaf node. So from here you can see that you can further break down this tree into further subtree until we get no node or only like single node, no further child node. So therefore binary search tree is a recursive data structure. So using this concept, we are going to use the recursive approach. So before I go into the recursive approach for this particular problem, first I want to go through this recursive general approach. So regardless of which problem you solve for using the recursive approach, it could be either array, or it could be either linked list or binary tree. Any recursive data structure, you can use this. You can use these 3 steps. First step, base case. Base case or the stopping case. That will stop the recursion. We need the base case. Without the base case, it will go into infinite recursive call, and then we will have a recursive like Stack Overflow error. So we need that. So explanation is, base case value, we must have that. So it could be either 1 or 0 or null, or some sort of discrete value. So that is the step 1. In step 2, in this step, we need to determine the general case, decomposition. So what does that mean? It means that does each recursive call that we are calling to the function involved a smaller case of the original problem leading to the base case? So in the recursive approach, we are calling the function itself. So does that smaller call that will need to lead to the base case? Step 3, composition. Does the smaller problem answer form the answer to the larger problem that need to form correctly? So these are the 3 steps. So based on that, let's go through this algorithm for this particular problem, binary search tree. So in the base case, we first have to check if the root is null. Then that is one of the base case. The root have to be equal to it could be equal to p, or the value that we are finding, or Q. In that case, this is so P and Q, if they are equal, then it is one of the cases that we have checked previously. In that case, then the root, we can just simply return the root because we found the root. So that is the base case. Next, we have to decompose. So in the decomposition step, we have to find in the left subtree. It could be in the left subtree. It could in that particular left subtree, there could be both P and Q by calling the function itself. And we also have to find that also on the right subtree. So both P and Q could potentially be on the right subtree, or only P and Q in the right subtree. So regardless, we have to find it. So this is the decomposition step. Next is the composition. In here, we check. If we can't find in the left subtree, we have to return right. We have to return right, and then we can go from right. And next is, if we can't find in the right subtree, then we return left. Otherwise, then we will you have found either both P and Q in both subtree, or you can you found it, and then you will it means that the root is the current node, so you can return the root. So let's have a look at the algorithm. So this is the first step. Root is null, root is equal to P, root is equal to Q. In this case, we can return root. So this is the base case. Step 2, decomposition. We check. We are checking in the left subtree by calling the function itself in here. Let left is equal to lowest common ancestor. In here, we are passing in root.left because we want to check for the left subtree. Same thing in here. We want to check for the right subtree, so we will initialize the variable and we check on the right subtree. Last step, composition. Composition is we check. If the left is null, then we return right, and the call will come back to here, and we will keep checking for the right side. Same thing again. If the right is null, then we will return left, so we will keep checking on the left side. Otherwise, then we will return the root. So in terms of time and space complexity, time complexity is O of n in the worst case in case of the skew tree, or O of log n in the average case. In terms of space complexity, because of the recursive call stack that I will go through in part 2 of the video, it will be O of n. So I'm going to make another video, and in the part 2 of this video, I'm going to go through the algorithm, the call stack step by step, so that you have a better understanding of this recursive algorithm. Thanks for watching.